Welcome to a new video. In this problem, we are given a first order differential equation. Notice it's first order because that's the highest order derivative that shows up. We're asked to determine if the equation is separable, if the equation is linear, and then to go ahead and solve this. Well, uh, I recognize that the way this is written is exactly like this. It's some function of x times the derivative plus some function of x times the original function equals some function of x on the right-hand side. And if your differential equation can be written in this form, then it's linear. Which, this is exactly the form to be written in to be linear. So the sine of x is a of x. The cosine of x is the b of x. And finally, the natural log of x is the c of x. So yes, this equation is linear. Okay, so yes, it is linear. We're also asked to determine if it happens to be separable. Okay, and it's not as clear to check if it's separable or not. So again, if we're going to check if something's separable, I like to write the derivative in the Leibniz notation, so dy over dx. I'm also going to move this term over to this side, because remember, you want to try to get the dy over dx by itself. So we get natural log of x minus y cosine of x. And then let's divide by sine of x to get the dy over dx by itself. And the reason why I do this is because the definition of being separable means that you can rewrite dy over dx as a function of x times a function of y. So can we do that here? Can we write this right side as a function of x times a function of y? And the problem is going to be that this y right here, you cannot factor it out from both terms in the numerator. And since you cannot separate the y from the x's in the numerator, you cannot separate the y from the x's on the whole right side, which means indeed in this case it is not separable. Okay, so not separable. Well, good news. Since we're asked to solve it, we know it's linear, which means we're going to end up using the linear technique. And if you're going to be using the linear technique, the first thing you should do is you want to write your equation in standard form. So what is standard form? What that means is you are going to make this coefficient in front of the y prime equal to 1. So you're essentially going to clear coefficients, and you will get this. 1 dy dx plus some function of x times y, which that function of x we called p of x, equals q of x. The given differential equation is not in standard form because of this sine of x term. Okay, so we need to go ahead and divide everything through by the sine of x. So let me rewrite the differential equation down here. So we have sine of x times y prime plus, I'm going to put that cosine in front, times y is equal to the natural log of x. Okay, and now let me give myself a little bit more room here. Now we're going to divide through by sine of x. And the reason why we do that is to put it in standard form. So we have dy over dx plus, well, cosine over sine is cotangent times y is equal to the natural log of x over sine of x. And what's the idea behind the linear technique? Well, that's where you want to calculate the integrating factor, which we called mu. And mu, its formula is e to the integral of p of x dx. So this p of x here, the coefficient of the y function in standard form, is what gets thrown into this formula for the integrating factor. So in our example, cotangent of x is our p of x. So this is p of x. So let's calculate mu. Mu is equal to e to the integral of cotangent of x, which we might see this better as cosine of x over sine of x. Because then how do you calculate this antiderivative? And the answer is you use a substitution. U is equal to sine of x. Du is equal to cosine of x dx. And this works out perfectly. So this cosine of x dx is exactly the du. So this integral here is e to the integral of 1 over u du, which makes this problem quite nice. So mu is equal to e to the natural log of the absolute value of u. Remember, you do not need a plus c when you are calculating the integrating factor. And the reason for that is it's going to end up canceling at the end. So this is e to the natural log. Actually, let's go ahead and simplify this because this is really nice. This is just u. Okay? Because e to the natural log cancels one another out. So we just get u, which is sine of x. So this is our integrating factor. What do we do with this? Well, when you multiply through by this integrating factor, this left side here, after you've multiplied through by it, turns into the derivative of a product. It will always be the derivative of the integrating factor times the dependent variable, which in this case is y. So that left side, well, once you multiply through by it, will be the derivative of the integrating factor times y. And let me show you this. Because in fact, if you multiply back this equation back through by sine of x, you get back to the original equation you started with, which is this equation from the very beginning. And I claim that this side here, that is the derivative of the integrating factor times y. It is a coincidence in this problem that after you multiply through by the integrating factor, it goes back to the original. But I do want to show you that this formula will always work. Once you multiply through by the integrating factor, the left side will always be the derivative of the product of the integrating factor times the original function, or the dependent function. So the product rule says you leave the sine of x alone, and you multiply by the derivative of y, which is y prime, and then you do it the other way around. Now you take the derivative of sine, which is cosine, and then you leave the y alone. And notice that's exactly what the left side is. So this left side here is the derivative of this product. So we are correct here. And then don't forget, we also have to multiply this side by sine of x. So we have the natural log of x over sine of x times the sine of x, which very, very nicely, these two cancel, and we get this equation. The derivative of the sine of x times y is equal to the natural log of x. Okay, remember, our goal is to solve for y. So how do you do that? Well, you just need to undo everything that's happening to y. It is being multiplied by the sine of x, and then you take the derivative. And we're going to undo those in the opposite order. We're first going to integrate to cancel off the derivative. So now these will cancel. And you get sine of x times y is equal to the integral of the natural log of x. All right. How do you integrate the natural log? Well, this brings us back to our Calculus 2 days. Anything that involves a natural log, you should be thinking integration by parts. And the trick is that the u is the polynomial in this case, and the dv, I'm sorry, put that the other way around. The u is not the polynomial in this case. The dv is just 1 dx. So the reason why we choose u to be the natural log is because its derivative has no more natural logs in it. It's just 1 over x. And when you integrate 1, you just get x. So this right-hand side is u times v, x times the natural log of x, minus the integral of v du. Well, look at this. These cancel, and you just have dx, which we get x times the natural log of x minus, well, the antiderivative of 1 is x. We pull a plus c, and this left side remains unchanged because all we did was integrate the right-hand side. And there's our solution. Well, we can make it explicit, and with linear differential equations, you should make it explicit. You should solve for y, which means our final solution, our general solution, is x times the natural log of x minus x plus c all over sine of x. So I hope the solution to this linear differential equation has helped somebody. Thanks for watching.